minutes was all waffle, so. Okay, so I think there's a big variety of levels of expertise in PDMPs in the audience, and I think some of the more expert people will be bored by some aspects of my talk, and I'm sorry about that, but hopefully I'll give some feel for some of the sort of interesting, and I'd say very exciting developments in sort of a theory of PDMPs in recent years. There's collaborators there which I'd like to acknowledge. There are others in the audience who I'll mention actually, and when we sort of get to sort of bits and pieces, but this is very much an overview. And as is the spirit of the whole workshop, please, please, please stop me and interrupt me and challenge me and ask questions and have as much dialogue as possible. And I promise I'll just finish after an hour and go on. Okay. The point, yeah, thanks. Okay, so good. Okay, so yeah, so I'm going to give it's something of an introduction, but I think I'll be keeping that relatively short because I think you've had excellent introductions from Manon and from other talks this week. I'm going to basically use three running examples, which are, I mean, it's nothing like sort of an encyclopedia of PDMP versions, but they're three sort of slightly different ones which have different sort of characteristics which are sort of worth kind of bringing out. And I want to talk about some of the sort of basic properties of these, so one thing that's interesting about PDMPs from a theoretical point of view is that it's a sort of blank slate. I mean, so when people started studying PDMPs, there was very little known theoretically. When people started doing MCMC, they just constructed a simple Markov chain, which instantly you knew had the right station distribution and things. So there are all sorts of sort of interesting new little kind of theoretical questions that have emerged as a result of PDMPs, which I think are very interesting. And they have practical implications, so they're not just sort of technical sort of things that we fill in. So I'll talk about some ergodicity results, and I'll talk about some very recent work on the robustness or sensitivity of PDMPs in the presence of sort of correlation and isotropy of other kind of kinds. And this is very, very preliminary work in the sense that, you know, we've made progress on particularly interesting cases, but the extent to which we can actually use those results in sort of very, very general complicated problems is very limited at the moment, but at least I'd like to share some of those ideas with you. Okay, so this is piecewise deterministic Markov chain Monte Carlo. Okay, so in general, we have an ODE, which is our deterministic dynamics, and then we have an event rate, and the event rate happens at some state-dependent rate lambda. This is my notation. And transitions between the distribution of these events, what happens is you kind of jump to another state. And of course, as we know, this is the sort of thing that you get in general. So where did I start this one? I started at the top here. Oh, no, I didn't. I started at the bottom here. And I moved up here, and then I made a jump. And on this particular PDMP is actually discontinuous, and therefore it sort of jumps down here and then it makes another leap. So this is an example of a PDMP. The PDMPs that are actually used in certainly in statistics and most statistics applications anyway, turn out to be continuous but not differentiable. Although there are some very, very interesting exceptions to that, but in general we would have ones which are continuous, which basically just change direction. Okay, so so the probabilistic sort of background to this goes back a reasonably long time. I say reasonably because, of course, MCMC was founded on probabilistic theory, which went back a lot further. But actually, so you can go back. I think there are papers before the very famous paper by Mark Katz on the telegraph process, 1951. It goes back, I think, later, even earlier than that, in fact. And it's a very sort of nice paper which on the mathematical foundations by Mark Davis, 1984. So this is that's the sort of background to it, but it's really relatively recently, at least in statistics, that these things have been thought of as a competitive method for doing Markov chain Monte Carlo methods. And one of the sort of interesting things about this is, I think, what a lot of the in statistics has been driven by theory. When MCMC was developed, back in the 50s, whatever, there wasn't a huge amount of theory to say these things are going to converge incredibly quickly. And theory has always been lagging behind practice in terms of MCMC in general. In many ways, PDMPs are sort of the opposite, in the sense that actually a lot of the theory that's been developed is actually sort of ahead of the curve in some sense, in the sense that it's talking about if we could implement these algorithms, they would be amazing. And a lot of the implementational questions, which are quite complicated, and some people in this room have actually worked quite a lot on them, are actually really sort of the bottleneck in terms of making these things very competitive in many sort of examples. And hopefully that will develop. Okay, so okay, so I don't think I need to talk. Manon, I'm sure you probably said all these things in your talk. So you're talking about non-reversibility of MCMC. But of course, in MCMC, one of the breakthrough of using PDMPs is the notion that we can actually get away with not satisfying detail balance relationships and to actually work in a non-reversible but tractable way. So because Hamiltonian MCMC, hybrid Monte Carlo, as some people call it, has already been sort of massively popular, probably the state-of-the-art method in MCMC and statistical problems these days, has a sort of non-reversible character, but most of its implementations actually are kind of reversible. But it has this kind of notion that it does have a sort of momentum that moves you around the space, and that kind of helps the mixing. So why does non-reversibility help? Well, okay, so which of these is important? Well, so the sort of what we really sort of understand is that if you actually have non-reversible methods, you can have some notion of momentum that moves you through a space. And so here we have a comparison of a random walk, which basically has a momentum type, changing momentum, but a momentum type behavior. That's the black trajectory, whereas the red trajectory is just a random walk, which doesn't have any momentum. And you can see the sort of black one sort of moves around a lot more than the red one does. But of course, that's not mathematics. The other thing you might hope to do is to actually escape local modes. And it turns out that non-reversibility is not particularly the thing you want to do in this context. It's actually hard to get to actually break multimodal problems. And there are other methodologies, which again have been talked about this week, to look at multimodes. But certainly in terms of breaking down sort of multidimensional random walk type behavior, which is this top diagram here, is something that non-reversibility can be very, very good at. Not necessarily going to be very good at, and sort of we're still, I think, limited understanding in terms of the interaction between non-reversibility and real high dimensionality, and what types of non-reversibility should work in different contexts. And the space of possible non-reversible methods that we currently use in Monte Carlo is a very, very small class of algorithms. There are many, many more things that could be tried and are probably feasible, but we're working on developing some of those, but not in this talk today. So I think it's very exciting in terms of methodology and in terms of theory, and I think applications too. Okay, so this is the simplest possible one. We call it the one-dimensional zigzag. What is the one-dimensional zigzag? What it does is, okay, so we just have a simple density pi here, which is one-dimensional. So basically, we have a switching rate which is equal to minus the current velocity, which is like plus or minus 1, times the derivative of log pi. And pi is just one-dimensional in this case. So if this is a unimodal density, which in this case it was, on the left-hand side it was Gaussian, on the right-hand side it was Cauchy, then we're in the situation that if it's moving away from the origin, then it has a switching rate, it tends to come back. And when it's moving towards the origin, it essentially cannot switch because the maximum of these two numbers is going to be 0. And that's true for both of these, and you can kind of see that the character of these are sort of fairly similar. You can sort of see the heavier tails from the county distribution here. One thing that is noticeable about this, and it actually came out in Georgos's PhD very much in terms of studying these things, if you look at PDMPs on heavy tail distributions, what can you say? So when we look at heavy tail distributions in MCMC, what we're really concerned about is the stability of excursions away from the probability mass. And in this case, the excursions here are relatively stable in a sense which I'm not really going to go into in any detail. But if this is a random walk metropolis algorithm, then these excursions would behave very much like a random walk, and they would be less stable. They would have less, the length of the excursion time would have less moments, and it would mean that the MCMC would be less stable in terms of things like ergodic averages. Okay. And so there are sort of interesting questions about stability, which PDMPs give you, but it turns out that, you know, if you have heavy tail distributions, then a vanilla PDMP, which has a velocity of plus or minus 1, can only buy you so much. Okay, so this is what in multi-dimensions, in this case 2, this is what the canonical zigzag actually looks like. Basically, it has a velocity which is plus or minus 1 in each component. And so therefore trajectories look a little bit like this mess here. Okay, so this is what trajectories actually look like. And I'm not going to go through the maths, but basically your switching rates, well, what are you doing here? For the zigzag, but essentially what you do is you just switch each component independently of any other component with a rate which is given by this. And this is essentially looking at the partial derivative with respect to that component, the ith component. Okay, so these things move around and basically they have 2 clocks with them. And these 2 clocks basically have an alarm which goes off, and one of them says change direction in one direction and the other says change direction in the other thing. So which is why you get these kind of trajectories. Okay, so what happens here, and it's not completely obvious, is but the invariant distribution here is actually proportional to pi of x. In other words, well, where's the v gone? Well, the v is uniform over the 4 possibilities. And in stationarity, this invariant distribution here is suggesting that you have independence between v and x. And this gives many advantages in terms of basically, you can always refresh the velocity by throwing away your current velocity and replacing it by something IID from the distribution of, you know, these 4 possible values here. So there are lots of flexibility in how you sort of implement these things. Okay, so this is so the marginal distribution is what we want, and this is a truly continuous algorithm. And a mistake that people sometimes make is to essentially just store the values at these kind of points at which you change direction. But that will give you bias samples. It's easy to write down what that bias is, and it's not necessarily small. Okay, and so in order to actually use it for practical MCMC, this is continuous time. So what you have to do is you have to have some exogenous method for selecting times at which to record your functionals of interest. Okay, and therefore you need some kind of way of constructing skeletons, in other words. And so, and there are various ways of doing that. And I'm not going to go into details about sort of implementation of those kind of things, but that's obviously something extra to think about over and above the sort of things you'd have to think about if you were just running a simple discrete time MCMC algorithm. Oh yes, and I hinted at this before. There's a lot more flexibility. For instance, you can certainly do the following. You can actually decide that when you're basically this is your this lambda I0 xv is what we call the canonical switching rate, and the canonical switching rate is the minimum possible switching rate we could possibly have, defined by in terms of, you know, being able to have the correct invariant distribution. But the interesting thing is that if you add on an arbitrary function here, which is only a function of the state and not a function of the current velocity, then this addition here doesn't bias in any way the invariant distribution of the Markov chain. So that gives a huge amount of flexibility, which you can use if you want. So it's interesting. So you might do that. So it turns out that one of the reasons that you might want to do that is for irreducibility. And I will be saying quite a lot about irreducibility later on. But it turns out that many PDMP algorithms have some kind of quite nasty reducibility properties, which are perhaps not obvious when you sort of first write them down. And partly caused by the fact you're in a larger space, you've got to worry about your velocities and things of this kind. So there are some sort of nasty sort of reducibility things you need to worry about. Certainly, if you add the capacity to sort of change direction in some sense independently of our current velocity at some arbitrary rate, that you give yourself more options. So you basically make it much easier to have irreducibility. Okay, so you can use that mathematically to prove things and actually in practice to get algorithms which are more efficient. Later on, I will say something about the problem of how do you choose, if you've got a choice of this, how would you choose the refreshment in order to sort of get reasonably efficient Markov chain? There's very, very little known about that, but we do have some theory in a toy example, which actually is quite interesting and quite surprising. Okay. Why might we not want to do this? Because you might think, well, actually changing direction seems like a great idea. But the more direction changes that we actually do, the more of a sort of haphazard sort of random walk type behavior you're likely to get for the process. And in fact, there's a beautiful paper by Andrew Duncan and Joris Berkins, who many of us know, basically who prove that in some appropriate sense, as you let the refreshment rate go off to infinity, what happens is the process starts to behave more and more like a diffusion. Okay, so there's a diffusion limit result for this as you look at larger and larger refresh rates. Okay, and that's not very, okay, so I should say a little bit more about that. When I say it converges to a diffusion, it converges to a diffusion in the X space. In other words, the V becomes irrelevant. And as a result of that, so actually the diffusion that you get is a reversible diffusion. So by increasing V, or nu, I should say, if you increase nu too much, then you're going to get much more of a kind of reversible character to your process. And any notion of non-reversibility that you were hoping to take advantage of will be lessened. So you really don't want to take this to be too large in some sense. Okay. There's another beautiful paper by Christoph Andrew and Sam Livingston, which gives a very precise statement. I might even have it later in the slides, I can't remember now, but which gives a precise statement about the effect of actually having a refresh on the asymptotic variance of Monte Carlo estimates. And the sort of the headline of that is that for the zigzag algorithm, okay, we have the other algorithms we'll introduce shortly, but for the zigzag algorithm, it turns out that basically if you want to optimize minimize the variance of your Monte Carlo estimates, what you need to do is you need to take nu to be equal to 0. Okay, so in some sense, the nu equals 0 is the most non-reversible. Nu equals infinity is the most reversible. So you have this continuum of algorithms in between the two, and the one which actually produces the best Monte Carlo estimates in terms of the smallest variances is by taking the most non-reversible. Okay, I'm going quite slowly, but any questions? Yeah. Sorry, could you say that again? You know how you had the reason yeah. Well, that could be one, yeah, motivation, yeah. Well, what are these? How do those problems? Okay, that's a great question, and can I answer it a little bit later? Because I think I might have some slides that talk about that. Yeah. Okay, right. So yeah, just I want to introduce two more algorithms. This is the bouncy particle sampler which has been around for similar amount of time in statistics, at least, and longer in physics, I think. And it has a very similar thing, property in that you essentially have a jump rate, which is the maximum of some quantity involving a derivative. In this case, it's just a gradient with a dot product of velocity and zero. Okay. And so what this does is when it decides it's going to change in its pure form, the bouncy particle sampler will essentially say, oh, I want to change direction here. It basically draws the contour, this contour here, that it's currently residing on, and then basically looks at the tangent to that contour and reflects in that tangent. So the bouncy particle sampler is something that basically does this, right? So it's very similar, and again, you can prove that it does the right sort of things. Again, you can add refresh. I introduced refresh with zigzag, but basically you can do it for any of these PDMP methods, and so you can use refresh as well. And so this is the bouncy particle sampler. Okay. Yeah, so this is a slightly more exotic one, which I've been interested in about the last, I suppose, 3 or 4 years, is ones based on stereographic projection, and a number of people in this room have been working on this with me. And so the interesting thing about, stereographic projection is something that's very easy to do. What are we really doing here? So suppose we had an algorithm on, a distribution which is a one-dimensional. Essentially just draw a circle, stick it on top of the real line, and then project up to the North Pole. Okay, this is very, very classic geometry, and basically we sort of and we identify the point on the real line with this point on the sphere. Okay, so this is something that you can do. Why might you do it? Well, essentially what you can try and do is you can try and take advantage of the fact that the sphere, or the circle in this case, is compact. So it may be much easier to construct algorithms that kind of get around. You can do this in higher dimensions as well. Something which I don't think I'm going to say about today, but if anyone's interested, I'd be happy to talk about. If you actually construct things like random walks on hyperspheres, they do have some very appealing high-dimensional properties. So we would call it the blessing of dimensionality of high-dimensional Brownian motion on a hypersphere. Very surprising properties. And the idea is that we might be able to construct MCMC algorithms that somehow inherit some of these properties. From a theoretical point of view, in some sense, the fact that the sphere has kind of curvature, which kind of brings points back together again, means that in some sense things aren't going to get any worse. And for some algorithms, when I say worse, in doing a comparison between the algorithm I would construct on the real line and the corresponding algorithm I would construct on the hypersphere, we do have, in some cases, theoretical results which basically say that the version on the hypersphere is always going to be more, at least as quick in some sense. So we do have results, but we only have those results for random walk metropolis algorithm at the moment. We don't have results, for instance, for PDMPs. But the intuition is clear that essentially working on the hypersphere is actually should give you advantages in terms of mixing of the algorithm. And the fact that you're basically working on a hypersphere, which is a very simple object mathematically, means that in practice these things can be implemented relatively easily. Yes, Mike. Yeah. So yeah, definitely. I mean, so the first paper that we wrote on this, we basically we concentrated. Well, we did a little bit on the PDMPs on that, but we also simulated simple random walk metropolis algorithms, which are actually very easy to implement. They're actually easier to implement than the PDMPs on here, because all you're really doing, you can really sort of take advantage of the fact that you're doing an MCMC algorithm on a manifold, but the curvature of that manifold is constant, so the geometry is trivial. Everything sort of works out, and you don't have any nasty formulae to basically worry about in terms of this. So implementing these things on a hypersphere is actually a very sort of generally not too bad a thing to do. I should say the negatives, right? So what negatives? Well, one is this is so I think some people might have already sort of seen that there's going to be an issue with the North Pole, right? Because what points are going to get mapped to the North Pole? Well, actually, everything in the tails is going to get mapped to the North Pole. Right? So whether you're in this tail here or this tail over here, they're all going to get mapped to the North Pole. So essentially, if you have too much mass in the tails, and you can do the maths, basically, there's a calculation in terms of how heavy your tails are, then you can have a density which is on the hypersphere, which basically blows up to infinity at the North Pole. It's mathematically, it's very interesting what happens there then, but it's not necessarily practically very good. What you'd really want to avoid that. So essentially, if you have the tails which are polynomial with a coefficient with a power which basically is too small, then essentially you get this kind of blow up at the North Pole, and that means that your algorithms couldn't get stuck near the North Pole. Okay, and is that bad? Yes, it's bad. I mean, it's no worse than you would do if you were doing random walk metropolis on the Euclidean space in the first place, right? In fact, it's better for reasons which would, but actually it is an issue. So we can't just, I mean, so really, I said that this sort of circle and this hypersphere, whatever, are compact, but actually, you really, of course, you're not including the North Pole. So actually, you have to include the North Pole to compactify the whole space, and so there is a sort of kind of question there. The other thing, I should say is that these methods are highly sensitive, well, are sensitive anyway, to how I choose this hypersphere, right? In other words, I've got two choices. Where do I position? Where do I kind of sit it on R to the D? Right? Where do I put? And common sense suggests I might want to sit it somewhere near the mode of the distribution or something. Turns out that's a pretty good guess, but of course you might not know the mode of a distribution. And if you don't manage to do that, then you will lose efficiency. The other thing is that how big should you make this hypersphere? You've got radius. Okay, and you can also, of course, you could have basically a covariance matrix. You could make it into an ellipsoid of various ways if you wanted to. But even just in one dimension, you get a radius. And depending on the size of things, if you make this circle very small, then there'll be a lot more mass near the North Pole. Right? If you make the circle really, really huge, then you'll be putting a lot more mass in the southern hemisphere. And it turns out there's a sweet spot, and you can actually characterize what that sweet spot is, but whether you can actually calculate, and that's in terms of something that you wouldn't necessarily know, and you might have to learn adaptively. Okay, so Cameron is working on adaptive methods for this, to use the kind of things that we know in order to sort of improve these algorithms and design new ones. Okay. I'm going too slowly, probably. Okay. Just want to show you what these things look like. Right, so here's the stereographic bouncy particle sampler. What are these trajectories? Well, basically, I've constructed the bouncy particle sampler along great circles on the hypersphere. And then what I'm doing here is I'm just basically reprojecting these down on onto R2. Okay, so these are the kind of trajectories that you get. On the left-hand side here, you see a SBPS which has no refresh. On the right-hand side, you have one which has refresh. Something you might notice is, and you might think maybe it's a coincidence, there's a sort of hole in the middle there. Yeah, and you might be thinking, is that an irreducibility problem? And the answer would be correct, it is. So you can have irreducibility issues here. On the right-hand side, this is solved. I mean, I can't prove this to you now, but it is solved by having this refresh. Okay, so I'm not going to, yeah, so some people, so Alice has a nice paper a few years ago, which is, it's not 2021 anymore, it's appeared now, and Filippo's paper as well. So a lot of people in this room have contributed towards a really important work, which I think is the bottleneck in this area of practical implementation. And so I'm going to just skip over that unless anyone wants to. And anyway, so Filippo and Alice know more than I do about it. So. Okay, so implementing these algorithms is a very, I think, active area, an important area. Okay, but so what I do want to emphasize, though, is why are people excited about this in statistics? Okay, there's a particular reason why statistics is because essentially what makes MCMC methods uncompetitive in the sort of biggest problems today? Why is it that machine learners are basically not doing MCMC routinely on all their problems, even though sometimes they claim to be Bayesian? And the answer is because it's just too slow. And why is it too slow? I mean, very often it's too slow because the data sets are just too large. Well, not too large, but they're large, and you don't want to ignore them. So if you look at all the standard algorithms in machine learning, like stochastic gradient descent and all these kind of things that they're doing, what essentially they're doing approximations on the basis of, okay, this is my capital N. Just think of it like this is the size of my data set. Okay, so what you're doing in things like the stochastic gradient descent algorithm or various kind of approximate versions of MCMC is to say, actually, maybe I need to calculate the gradient of a log of this thing. I can write that as a sum. So I'm going to, instead of actually computing the entire sum, I'll just produce an unbiased estimator of it. Okay, and it's well known that things like stochastic gradient descent do actually pretty well. And approximate MCMC algorithms also do pretty well, but this will induce a bias. Okay, so a lot of the standard, if you take your off-the-shelf MCMC algorithms and you try and implement them without computing pi at every iteration by using a cheap approximation, if you do that, you're going to end up with something that gives you a bias. How big is your bias? Who knows? It's very difficult to tell, and it's very problem specific, right? So your next data set comes along, it might be huge. This one, it might not be too bad. Okay, so that's a big problem. So subsampling is a great idea in principle. It means that these things become a lot quicker, but actually they cause problems, and basically they mean that MCMC algorithms in general are going to be biased. Okay, so yeah, so this is the kind of general philosophy. At each iteration, we only update a small number of terms in this product. As stochastic gradient learning approaches and optimization. So what might we do? So there are some sort of traditional, sort of quite old methods in MCMC, like pseudo-modular MCMC and things, where you might try and produce unbiased estimators of this. It turns out none of these work in the sense that none of them can give you an algorithm which doesn't have a computational complexity, which is at least capital N, right? And capital N is going to kill you in many cases if you have 1 billion data points. Okay, so PDMPs have this amazing property that you get subsampling for free. Okay, what do I mean by for free? Basically, you don't induce any approximation error. Okay, so let me go through the idea here. So it's very simple. Okay, so I'm working with log pi or its derivative. Okay, so I'm going to have to, in principle, for the pure algorithm, I'm actually computing this thing. But what I'm going to do is I'm going to take a subset of size 1, say. Okay, I'm just going to take one of these points here, and so essentially, what will I do? I'll just take this one data point, and I'll approximate this sum by this one data point as basically capital N multiplied by log pi I prime. Okay, I've written it in one dimension here, but doesn't have to be. Okay, so in this case, I only need to take one of my billion data points and get an estimate. Now this is going to be massively more noisy, and one would expect that the bias induced by this approximation would be large, right? Well, I'll come back to the bias in a minute, but just to say that the vanilla subsampling algorithm method is basically essentially just to take the obvious unbiased estimator here. A much better idea if you have some notion of the mode of your distribution or some notion of a center, and it doesn't have to be that accurate, it just needs to be something in the vicinity of the mode. So in other words, you have a pi star where we can do one single calculation of log pi prime. Okay, so instead of actually having to do this every iteration in my algorithm, I just do it once and I store that. So the control variate method essentially works by, well, it basically looks at estimating these differences, which has an order of magnitude smaller variance, especially in the case where you have posterior contraction, which you have in Bayesian problems, of most regular Bayesian problems. Okay. So anyway, these are two versions that you might use, and that's okay. So the first thing is that these algorithms are going to be different. So what am I doing here? I'm going to be using these estimates and sticking those into the formulae that I actually have to implement the PDMP. Okay, so the algorithm is going to be different because I'm going to have this random thing in there instead of a real gradient. So this is what we do. So basically, we put in there. So basically, this is what we'd like to use. And what I'm going to be doing is I'm going to be sticking in my approximation here. Okay. So what will happen? I'm going to have a much noisier estimate for my gradient. And therefore I'm going to have more switches. So this thing is actually going to be more sort of irregular. It's going to be less kind of sweeping moves. So that's something we might worry about. On the other hand, the miracle is that in terms of the invariant distribution, putting in an unbiased estimator in here actually you keep the invariant distribution of pi. Okay, so this is so how is that? How could that possibly be the case? Well, the reason why that's the case is because you can quite easily show is that the subsampling version of this, using this as our switching rate, is an algorithm which can be rewritten as the canonical, as one having the canonical one plus a refresh rate. And a refresh rate is a kind of correction that comes out of the sort of Jensen's inequality of looking at the expectation of this minus the expectation of this. Okay, so you can actually quantify what that advantage is. Okay, so this works in principle. Yeah, so we just said that. Okay, and so we have this. So we introduced this notion of super efficiency, which is a sort of it's a sort of headline grabbing thing, really. I mean, of course, there are issues in terms of how generally you can apply it, but we introduced this notion of super efficiency, which is you can have data sets which are so large that in principle you can actually run the MCMC algorithm, the entire MCMC algorithm, using these subsampling techniques, and you can run them to convergence using less compute effort than needed to do one full evaluation of the target density pi. Okay, and so this is a sort of a kind of an attractive idea, but of course it's only super efficiency because essentially the target density is just prohibitively expensive. and so it's maybe the advantage you're getting is not so much, but so this is a big advantage that you potentially get. This is just some examples very quickly. So this is some these are small data sets, really, so size 100 or 10,000, and basically what do we have here? We have so every circle, every red circle here, the compute time to compute the likelihood exactly once is essentially every time that compute has been used up, basically you draw another red circle. So basically you can see from on the left-hand side here the canonical version, which always computes the likelihood. I needed to compute the likelihood about, I don't know, 20 or 30 times before I sort of got lost in the red mass there. This was much better for the subsampling method without control variates. And here you see basically you get all the way into the mass before you start seeing these red blobs. And you get a much more clear picture for larger data set that here basically you get all the convergence all the way into stationarity, and you get that convergence happening before you've actually had to compute the likelihood exactly once. Other things to note about this, though, and you can see it probably clearest from this, is whereas the canonical zigzag actually, it kind of went in a pretty straight line here until it got lost in here, and then presumably did some other stuff. Here, there's quite a lot more shifts, right? So there's quite a lot moves around. And therefore, you can sort of see that the kind of character of the process is changing. And later on, I might say something very briefly about Sankit's work. Sankit's here, isn't he? Yeah, Sankit. About a very nice PhD he's doing on trying to mathematically characterize how much you lose in terms of Markov chain convergence. And this is just basically showing that the super-efficiency thing really holds. So basically, this is the effective sample size of your MCMC algorithm per epoch, and the epoch is the time taken to compute the likelihood exactly once, and just doing this as a function of the size of a data set. And the purple one is the basically curve, which basically is a straight line, which basically describes, sort of if you use the control variate zigzag, then essentially you get this efficiency gain. Okay, right. How much time have I? I don't want to. I don't want to outstay my welcome. Yeah, I did start. Yeah, and I've got. I mean, I've got sort of. Yeah, I've got quite a lot still to go. But I think. Any questions? Yes. Yes, please.
I have a question about the schematic. So if you have a very heavy, have some problem with the node. And the question I have is that a feature of the theoretic correction, or can you have another correction that in heavy tail case you can kind of escape that, or maybe there is some inherent problem that heavy tail case, but there is no way to specify which other correction.
A great question, very good question. Yeah. So first of all, the reason we use stereographic projection with spheres is because we can implement the algorithms easily. And it's very difficult if you have a sort of changing kind of curvature. Now, in principle, you could have things which look like, does this one work? You could have spheres that look like sort of, here's my space, and oh, no, that's not brilliant. Is there one that works, or do we know? Oh, thank you very much. Cheers. Yeah. Okay, so in principle, so there's your R to the D, right? So in principle, you could actually, project and have something that looks a bit more like that. So sort of you're spreading out the mass around here. You'd never be able to implement it. I think it would be very difficult to implement something of this kind. But you could probably do this in such a way that would stop the density from being infinite. But this might actually have to go, you never know, this might actually even have to go all the way to infinity. I don't know.
So there is no way to have a constant curvature surface and a mapping such that you can have a Hebbian distribution. Or there's no such mapping.
Okay, so Georgos may remember better than me, but I believe that the result about when the density, let's go back to the usual case of I believe the case that when we're using spheres, the condition on the tails of a distribution are independent of they're independent of where you put the sphere and the radius of the sphere, right? So if it has constant curvature, it's a sphere, right? So is that correct, Georgos? Yeah. So I don't think it's an easy fix. It's a great question. Yeah, but I don't think it's any easy fix. But we didn't try too hard thinking about this because I think the implementation of that sort of thing would be a complete nightmare. Yes, please. So if you move a sphere,
If you lift it off the surface, would that help with the details?
I think yeah. So it turns out that you can put the sphere if you actually levitate it above, what would happen then?
I think for the tape, equivalent to increasing the volume, if I remember correctly. At least I think Joe told me that.
Yeah. I think it's a good question. I think you still get the same. You get the same phenomenon, but it's not impossible. You'd improve things. So we have played around. So Sebastiano's been working with doing all sorts of interesting things in terms of perturbing these things. It turns out that if you put the sphere actually on the surface here, it's equivalent to putting the sphere with its center on the line, which doesn't look obvious, but the geometry is two lines once you do it. But I guess in some sense, there's no free lunch, right? You're mapping yourself from a situation of a density which has loads of mass near infinity, and all that mass needs to sort of come together. So you can't just kind of shove it in the corner and forget about it. It's kind of intrinsically there. But so it's still true that if I look at random walk metropolis on the hypersphere, transformed from a density on the real line or on R to the D, it's still true that you get geometric you get uniform ergodicity, in fact, for a much larger class of densities than you would do for the random walk metropolis on Euclidean space. So you're still a lot better off than Euclidean algorithms. Yeah. Sorry? Yes. Yeah. Well, okay. So right. So if you well, first of all, you almost certainly won't, right? But you might. Okay. And so there is a very interesting question. I mean, I don't know if any Markov chain people in the audience are interested in the notion of Harris recurrence, but there's a very interesting kind of question about Harris recurrence about these processes. I mean, the problem is that you can actually have, the probability, since it's a continuous time process, and what direction are you going to be going in? If you happen to be very unlucky and your initial velocity is taking you all the way to the North Pole, you can, if you're unlucky, just go to the North Pole and just stay there forever. But it turns out, so if you do it in one dimension, right? If you do it in one dimension on a heavy tail distribution, and basically you've got a mass there, it turns out that mathematically you can have a PDMP that basically goes all the way to the North Pole. The density is infinite, but it just basically kind of pauses there for an instant and then basically just carries on. In fact, what actually really happens is it sort of spits you out either this to the left or the right with probability half. So you might go back down that way, or you might go down that way. I say mathematically, so you can prove in one dimension this is what happens, nothing bad happens. How are you going to implement that? Good luck, because the rates of conversion to infinity up here, right? So that's absolutely crazy. So you don't want to actually do that. In multi-dimensions, it's worse than that, because you can actually have a situation where the singularity is so large that it absorbs you. Black hole. And so what actually really happens is that, you know, I'll just draw another diagram. So yeah, there's your North Pole, and you've got camera coming down from it. If you start here and you're going in this direction here, you might have a sort of near miss where you basically go very close to North Pole. Well, this bit, I don't know if you can see this, but this bit of the trajectory here will be very expensive. Right? And also, I mean, it could be that actually you sort of do a lot of jiggling about. Yeah, so this, the questions, the mathematical questions, actually, the PDMPs come out with flying colors. That generally they do really well. But the implementational ones, they're going to be very sensitive to this. So in the way that the random walk metropolis gets you in a more basic way, the PDMPs can be bad. So as long as, but it turns out that, you know, there's so little mass near the North Pole that you know, if you don't start, you know, on a collision course for it, then you're just not going to go there unless you've got a really, really heavy tail distribution.
That means found in the requirement that you need conversion on velocity.
Yeah. So you definitely could in principle, right? Because you don't, you know, if I look at the overall target distribution, you can look at that distribution and condition on, you know, bringing in +1 space or -1 space or something. That's fine. If you can sort of do that. But computation is not going to be any better. Any more questions? I'm sort of yes.
Could you move the capacitance requirement on this sphere? A sphere with a hole in it, North Pole, and then maybe adjust your MC moves. If we're going directly to the North Pole, cap the distance is small. So it's basically effectively impossible to get to the hole, the North Pole. That makes sense. So adjust your metric.
Yeah, you could. Yes, you could do that. But then, how are you going to? You need to get away from there, right? That's
so
something.
you can go back and forth. So you basically give up you have a varying metric where in the opposite direction you move faster.
Yeah.
Along kind of circles that are parallel to your projection. That's stay constant.
Yeah. So you could do it, but remember that we're actually trying to run this in continuous time. So there's no actual step size or anything like that. You don't kind of have the freedom. Yeah, and yes, actually. So one thing I skipped over the sort of practical implementational side of this, but actually I think a lot of the interesting practical implementational things these days are based around approximation by discrete time things, some of which have adapted step size. So yeah, so I think they're interesting things you could try on that. Yeah, but I mean, so the North Pole issues you can't ignore, but they're not. In some sense, they're just a different way of packaging problems that we always have when we have a density on R to the D, right? I mean, you know, infinity is always a long way away, and if we happen to put infinity at the North Pole, it's still going to be an issue. It's just transformed. Right. So so I want to do a little bit. I'm about a quarter of the way through, but I'm not really. I'm probably about half, but I'm not going to do it all. But what I'd like to do, I'd like to say something about ergodicity, because there's some very good questions before about ergodicity, because some of these results are quite surprising. And well, at least we were surprised, and maybe people here will think they're more obvious. So I'm just going to look at the zigzag algorithm, and we're going to look at an example. Right. So here's an example, right? So this is a two-dimensional, and so I actually I ask you the question: does this mix? Has this zigzag mixed? Well, you can't really tell because you don't know where the support of the distribution is, but I can tell you that the support of distribution really is just around here. So, so it looks like things are going okay there, but it turns out that this is a counterexample which basically shows a zigzag process which is not mixing, and I'll show you why. Well, no, actually, maybe I won't show you why. Can anyone see why?
Very sorry, I'm not answering your question.
Oh.
Lydia and I were supposed to start at 2 o'clock, but I think we can give up a bit of time. Maybe one.
Okay. No problem. Yeah. Well, I did start late. I did start quite a bit late. Yeah. So I was only planning to talk for another 5 minutes. I always keel over after an hour anyway. So don't worry. Yeah. But now you have to answer my question. No. So, yeah. So okay. Can anyone see why this zigzag is not converged? Yeah, exactly. Yeah. So this is going. Yeah, it's counterclockwise. So this is a counterclockwise. So this is actually not exploring the entire space, and this is very related, Michael, to your questions of last week and today. Actually, because the invariant distribution of the limiting distribution of the x's is still correct here. And the reason why, basically, because of this particular distribution, you can only go around clockwise and you can't. It turns out that you're not allowed to change direction until you get beyond the point at which this is the center of a distribution. And I'll tell you what the distribution here is. This is the distribution, okay? This is the distribution e to the minus the maximum of the modulus of x and the modulus of y. Okay, and this is, you can sort of, work out quite easily what's going on here, and you always go around anti-clockwise if you start anti-clockwise, or clockwise if you don't. So basically, this is an example to show that the zigzag has some potential irreducibility issues. So the question would be, well, can you somehow? I mean, so in this is a bit of a this is a problem, but it's if you genuinely were interested in this distribution, that wouldn't matter, because actually the conditional distribution clockwise or not, or anti-clockwise, is the same, and it's what you want it to be. So it's very interesting, because we tried very hard to try and modify this particular example. By the way, these squares here, they're essentially just the contours of the density. Yeah. So for instance, by sort of smoothing over these contours, and it turns out that if you do the smoothing over, then you immediately make it irreducible again. So what I'm saying is that we were unable to produce an example, a counterexample for the zigzag, which was smooth, basically, that was differentiable. Okay, so this density here is continuous but not differentiable, and so that's kind of interesting. And the sort of positive thing about this is that there is, of course, you can solve this. You can solve this problem even on the left-hand side by having refresh. And I can always do a refresh, which basically says, all right, I'll just start going around the other way. Right? I can always do that. But as we saw before, refresh is not something you want to do in an ideal world, because actually it's reducing, in some sense, your tendency to be non-reversible. So the only other thing that can go wrong here, and this can happen, is we can have this kind of evanescence property where we have ridges of probability which get thinner and thinner and thinner and go off to infinity. Right? And if you happen to be unlucky enough to start on one of these ridges, then basically you can sort of not converge. So this is a result that we came up with a few years ago, and it doesn't sound, it looks quite sort of trivial, but it turns out the proof is quite long, quite complicated. And so what do we have now? I'm sure this is not best possible, but it's certainly the best that's known at the moment. So basically, if you have a smooth enough density, we assume C3. I'm sure you don't need C3, but I think you definitely need C1. It basically the density converges to 0 at infinity. That's not unreasonable. And then this is the third condition which we needed. And if anyone's really interested in why we need this condition, I'd be happy to talk about it, but I don't have time now. We'll have a non-degenerate local maximum. In other words, there is some local mode within the distribution, doesn't have to be the global mode, which has the property that at that mode, if you compute the Hessian, it's a non-negative, strictly negative definite matrix. Okay, so that excludes things that look like, x to the 4 and things of this kind. Then basically you get the sort of irreducibility in a period, well, just irreducibility that you need for convergence. So one of the reasons why that's interesting is because if you look at BPS, and I think I'm going to sort of kind of stop after this slide maybe, is that if I look at the bouncy particle sampler has some quite serious reducibility issues. And with I don't have time to go into it, but theoretically we understand those reducibility properties a lot better than we did before. And actually these reducibility properties get worse as dimension increases. And so this is the sort of thing that happens with the bouncy particle sampler. Often the samplers basically go around like this and they basically miss a chunk in the middle, a bit like the plot I showed earlier. Maybe I even have a plot. Do I have a plot of this? No, I don't. Okay. Okay, so therefore basically you have this reusability in the sense that you'll never go to this region at all. Now, unlike the example with the zigzag, this is a serious issue because this will be giving biasing on the X space. And so you get so even for sort of simple normal distributions, then you get these kind of problems happening. And of course you can solve those by having refresh. And as we said before, you want to sort of optimize the amount of refresh that you basically add. Okay, so we've done work on this. We've done work on sort of how to optimize the amount of refresh that you do, and sort of try to explain in a high-dimensional context exactly what's really going on. And the BPS has some really interesting properties in terms of some components of its trajectories converging at orders of magnitude quicker than other components. And it's all related to this kind of small dimensional properties that you can kind of see in this diagram here. So we're beginning to understand really sort of the issues behind all of this. Okay, I haven't had time at all to talk about lots of other things, but I guess if we're sharing slides, if anyone's interested, there's probably another 2 hours and rest of the slides, but interesting stuff that you might be, and I'd be happy to talk about anything else. So, all right, so I'll finish there. So thanks for being a good audience, and thank you.
One question, maybe? Yeah.
Right, okay. 1 hour. Thanks, Manon. Yeah, okay. So this is one thing that that we're really interested in at the moment is to try and understand. Many algorithms have this property that if you have isotropy, if you have strong dependence, essentially they get worse. Now that's pretty much true of Gibbs sampling, Metropolis algorithms, HMC, virtually all algorithms we have, and in fact many of the least sensitive algorithms are the simpler ones. So trying to understand what the robustness of these kind of PDMP methods are to correlation structure is something that we're really trying to understand. So we have a paper with Joris and Kengo that is actually trying to really look at toy examples, but to understand them really well. And the stories are quite surprising. So for instance, if you look at this situation, where we're looking at a situation where we have like just normal distributions in arbitrary dimensions, but we're basically where I basically let the covariance matrix is this, and I'm going to let epsilon go to 0, and I'm going to look at how the algorithms behave. And it turns out that it's a good story for the bouncy particle sampler, because the bouncy particle sampler has slightly more robust properties in the sense that its convergence time scales as 1 over epsilon, whereas the zigzag sampler converges usually at order 1 over epsilon squared. Okay, this is just toy examples, but even this is like a 50-page paper to actually do all the calculations. But I think it is saying there's some kind of fundamental ideas about what these trajectories look like and what they will, and some of the the limiting processes that you end up with are non-trivial, and they're not sort of what you'd sort of expect. So it was an interesting journey doing this work. And I should say that, if anyone's aware of this, there's this very beautiful theory by Greg Pavliotis and Andrew Stewart. And they have a book in 2008, which does this averaging and homogenization techniques. Really useful in MCMC for situations where you have bits of your Markov chains which are converging much more rapidly than other bits, right? And so this theory allows you to sort of explain mathematically what really happens in there. Essentially, it allows you to use the idea that basically you've got a slow part of your MCMC and your fast part of your MCMC to make rigorous the idea that you can sort of average over the fast bit so that you just have something that's marginally over the slow bit. Okay, and there's a whole book to justify that, and this is the book. Sorry, it wasn't a short answer, but it's, yeah, thanks. Yeah.